Hi, everyone. Welcome. My name is Ben. I'm a tech support engineer for Axiometric Solutions. Particularly, its two brands, Audio Precision and Gross Acoustics. And I live in Portland. I originally started with AP as a quality assurance engineer about 15 years ago. So yeah, I love this company, and I'm glad to be with you all today. Just briefly, if you don't already know, Axiometric Solutions is comprised of three different brands: AP, Gross, and IMC. And we're a leading provider in the test and measurement space. We're also a global company, so we do support and have distribution channels in over 35 countries. If you're new to APx and would find a more general software training helpful, our global workshop series is already underway. You can find more info on the events page of our website. So in today's webinar, we'll consider primarily what methods are available for routing audio into or out of an A2B network using an APx audio analyzer. I'll do some demos, show how to make some actual measurements using a couple different devices, showing you the workflow and how the different tools work together. We'll look at some of the attributes of the different test solutions that are available, so you can select the one that works best for you. And then we'll wrap up with a time for questions. And as Jen just mentioned, you can submit your questions anytime, either now or at the end is fine. Okay, so just very quickly, since most of you probably already know, A2B is a technology developed by Analog Devices, which stands for Automotive Audio Bus. And it's primarily used in automotive applications and allows for up to 32 channels of bidirectional digital audio with deterministic latency. A few years ago, Analog Devices released a bus analyzer to support the design and debug of both 242X and 243X based networks. And the bus analyzer can be used for both node emulation on the network as well as network monitoring. And you can emulate either a main or a slave node in the network. It can also be operated either standalone by itself or PC controlled, and it's configured via the Bus Analyzer app. The Bus Analyzer is useful for audio test because it gives your APx analyzer a way to interface with the nodes on an A2B network. And it allows for any APx analyzer to be used as either the signal source or as the acquisition system. Interfaces on the analyzer include this two-channel speed interface via the Toslink connectors, as well as the file input capabilities of the bus analyzer software. So that allows you to stream audio to or from the network using a WAV file. So for example, using file output, you can simultaneously record up to 32 microphones to a WAV file for analysis in AP. So in other words, the AP analyzer role is to generate the audio stimulus and to acquire the output signal from the network and to produce the desired measurement results. And the bus analyzer makes all of that possible by providing a mechanism to stream audio into or out of the network. So to use your bus analyzer, just to give you an idea of the workflow, you'll first need to incorporate it into your A2B network using the Analog Devices Sigma Studio Plus software. So there's a plugin you can install that Analog Devices provides that adds A2B functionality to the software. So once that's installed, you can just drag and drop the bus analyzer node onto your canvas. After that, you can configure your stream routing, selecting which A2B audio streams to route to or from the bus analyzer. Once your network is complete, you can connect to the bus analyzer using the bus analyzer app and start the network emulation, at which point you can configure your audio streams, which audio streams you want to source or sync from the bus, or which interfaces you want to source or sync the streams from. And then from there, all you need to do is select your appropriate input and output connectors in the APx software, after which you can add and configure and run all of your desired measurements. So in our first demo, I will be measuring these two microphones here, MEMS microphones, on a bus-powered 2428 A2B transceiver. Here you can see a diagram of my connections. The towards master port on my MEMS board connects to the towards sub port on the emulator side of the bus analyzer, which will be configured to route audio from its SpeedIF output to the APx analyzer optical input. The audio analyzer is also driving a loudspeaker, which will generate the acoustic stimulus. So the stimulus is picked up by the mics, routed to the bus analyzer over A2B, and is sent back to the audio analyzer for analysis, forming what we call a closed loop connection. And just a quick note that for all the demos I'll be doing, the standalone switch on the bus analyzer will be set to off, which allows for the bus analyzer to be controlled from the my USB connected PC. So here's a picture of my setup. As shown in the diagram, the test board connects to the bus analyzer via a twisted pair cable. The audio from the board is then routed from the bus analyzer to the digital optical input on the AP, and the first analog output channel on the AP drives my loudspeaker. I'm using a 516, but you could substitute any AP analyzer with an optical SpeedIF input. So with that said, I'll go ahead and start the first demo, which will begin in Sigma Studio Plus. All right, so here you can see the network I've created. It's comprised of just two nodes, the bus analyzer node, which is set to emulate the main node, and one slave node, which is our device under test. I've defined a single 48 kilohertz, 24-bit, two-channel stream for the PDM mics, which is configured to stream audio from the sub-0 node to the main node. In the bus analyzer app, the first thing I'll do is create a new project. And enable the standard power emulator. From From here, we can connect to, I can connect to my bus analyzer. And my node is a 2428 chip, so I'll go ahead and select that. I also want to emulate the main node. And before I can start emulation, I need to select a network config file. So I'll select this .dat config file that I already exported from Sigma Studio. And now we can start the emulator. For this test, I'm going to select SpeedIF as the output interface for both of our streams, which carry the signals from our MEMS microphones. From here, I'll tell my analyzer, my audio analyzer, to measure on its SpeedIF optical interface, as well as to output on the first analog unbalanced output channel. And I have that channel connected up to my loudspeaker. Because this is a closed loop configuration, we can measure the input to output delay, as well as the input to output phase, and interchannel phase is also available. In addition to the frequency response, the delay, and the phase, we can also measure the total harmonic distortion, THD plus N, and a number of other parameters. In addition, all of our other standard measurements are available just like for every other kind of device under test. If you need to measure more than 2 channels simultaneously, the file output feature of the bus analyzer can be used to route audio streams to a WAV file on the PC rather than back to the optical input on the AP. So this allows for many more MEMS microphones or other signals to be measured simultaneously, up to 32 channels. So with that said, let's go ahead and take a look at how to perform high channel count measurements with a bus analyzer and an APx analyzer. For this demo, I've modified my network to stream 16 channels of audio. Again, from the subnode to the main node. I'll again select AD2428 as the transceiver type and emulate the main node, and then browse for my new configuration file. This time, instead of routing the streams to the speedif output on the bus analyzer, I will route the audio to a WAV file. And we can do that by selecting File from the list. The bus analyzer allows for recording up to 32 channels simultaneously to a single file. But for this demo, we'll stick to 2 since we just have our 2 MEMS microphones. This time, I need to tell my AP to measure from a file with digital units. So we'll select that as our input connector. And the output will be the same as before. I can hear the signal from my speaker, so I'm going to go ahead and add my measurement. Now that the AP is ready, I need to tell the bus analyzer where to output its WAV file. And then I can start the recording. Once that recording's going, I can click Generate, which will output a pilot tone followed by our configured sine sweep. So we'll stop that recording. And now in my AP, I can pull up the Choose Files window and browse for that file that we just saved to disk. To measure phase with file input, we'll need to use a different measurement. The transfer function measurement can produce both the magnitude and phase spectrums when measuring from a file using noise or any broadband stimulus type. So far, we've only been looking at how to route audio upstream to the to the audio analyzer, using my MEMS microphones as an example. But it's also possible to do the inverse, which is to route audio downstream to an output node, such as an amplifier or a loudspeaker. So to demonstrate this, I will measure the 3.5 millimeter analog output on my same board. This time, the speed of output on the APx analyzer routes to the bus analyzer input, and the analog output from the node routes back to the analyzer analog inputs. So once again, forming a closed loop connection, just in the other direction. Here's a picture of my setup. The AP speed of output wraps around to the speed of input on the bus analyzer, and the 3.5 millimeter output on the board connects back to the analog inputs. In this demo, I have my same two nodes, as well as a single two-channel stream, just like before. However, this time, I have my stream configured to route audio from the main node to the subnode. This time, we need to tell the bus analyzer where to source audio from. So I'll select SpeedIF for both streams. And in APx, we need to select SpeedIF as the output. I'm measuring 2 channels of analog audio, so that's already correct. So let's just make sure everything's working. I can see that there's no signal. So for my particular board, what I have to do is load a configuration file for the codec on the board to make sure it properly routes the audio. Right, so now the audio is coming out of the analyzer into the bus analyzer, being routed over A2B to the eval board, and then routed out of the 3.5 millimeter analog output. For non-acoustic measurements such as this, we might use the continuous sweep. This uses a sine-based stimulus and can be used to measure the frequency response, the phase, relative to channel 1 or input to output as before, as well as the group delay, PhD, and other parameters. If we want to measure the input to output delay, we can add another measurement called DUT delay. which measures the delay per channel using either a pseudo-random noise sequence or a maximum length noise sequence. One final way of testing an A2B device is to interface directly with the board via I2S or another serial interface if your device supports it. And the nice thing about this approach is it negates the need to use a bus analyzer, since you can do the test just by connecting directly to our digital serial I/O module. So using this digital serial I/O or DSIO module, the AP can transmit or receive audio from a node, again using I2S or another serial format, using either the device or the AP as the clock source. So to summarize, there are 3 ways of interfacing with an A2B device. SpeedIF supports 2 channels and allows for closed-loop operation, which, as I mentioned, enables the possibility of measuring input-to-output delay. File supports up to 32 channels. It comes standard with all of our analyzers, but it's open loop, and so you can measure inter-channel phase, but you can't measure the input-to-output delay. And then lastly, I2S, or digital serial, allows for up to 16 channels, negates the use of the bus analyzer, and is closed loop, which again allows for input-to-output delay. One thing I'll add is that all of these interfaces can be used to measure frequency response, distortion, inter-channel phase, noise, and a number of other parameters. Our SpeedIF and serial interfaces can be added to any modular analyzer with an empty interface slot, which includes pretty much all of our analyzers. Here are 2 example configurations for production test of either an A2B speaker assembly or an A2B microphone. Starting with the configuration on the left, the 517 was chosen because it has 2 microphone inputs that can supply either CCP, also known as IEPE, or phantom power to a connected reference microphone, but also because it has 1 modular interface slot where either a SpeedIF or serial interface module can be installed. A cheaper alternative is our APx500 Flex analyzer, which allows you to pair our measurement software that I just showed you with any ASIO-compatible sound card. So in this case, I would select a sound card that supports SpeedIF over Toslink, such as the one I have pictured, the Fireface UCX. If you are using a reference microphone and want to avoid buying a separate signal conditioner to power it, you can use our AG0003 adapter to power the microphone using the sound card's onboard 48-volt phantom supply. We do also sell a large variety of acoustic accessories, including a head and torso simulator, a wide variety of measurement microphones, and mic power supplies, as well as other accessories. And if you'd like more information on that, you can find it on our website. A quick note, for assistance with, well, we can only sell and provide support for our own products, Axiometric Solutions products. So for assistance with Sigma Studio Plus, or the A2B Bus Analyzer, or the Bus Analyzer app, I would advise reaching out to Analog Devices. Lastly, I've included a link to a technical note which describes many of the things that we looked at today. So if you would like some hard materials to refer to after watching this webinar, this will be probably the best resource for you. Okay, so that concludes our webinar. So we'll now take some time to answer your questions. If you haven't yet submitted a question, no worries. You can still do that by clicking the icon with the question mark in the top right corner of the GoToWebinar window. So let me go ahead and bring that up. All right, I see one question on measuring input to output delay that I think is already answered. Is the AP application compensating the latency of the A2B bus analyzer? No, we're not. We're measuring the complete input to output delay of the whole system. So that might be something that Analog Devices could provide. We do have a way to compensate for delay in our software, as what's called the .delay field in signal path setup. So you could enter a delay value there, but you would need to find that value from Analog Devices. So one person asks, I'm trying to automate my audio measurements by integrating control of my test equipment into a controller app that I use on my production floor. Will this work for A2B? So APx software, our software and measurements they have a complete API that you can use to programmatically control any function of the software. I also believe that the bus analyzer has an API as well. So for help with the bus analyzer API, I would contact Analog Devices. But if you need help automating our stuff, I recommend that you watch our webinar on the API that we have on our YouTube channel. That would give you a great head start. Otherwise, you can reach out to me and my colleagues at the tech support email you see on your screen. We'll be able to help you out. We have another question. Can the analyzer be used to connect to an existing car audio system for measurement? So yeah, you can test a car audio system. It just depends on what inputs and outputs that system has. If you can, connect in, if you can add the bus analyzer node, that's one option. If you can't do that, then maybe a direct serial connection using the DSIO would be a good option. And there might be other ways to get into it really depends situation to situation. I would say if you have a particular thing that you're trying to test, please email us with the specifics of that. It would be easier for me to help if I can have a bit more information. Regarding I2S measurement, is a USB-I module necessary to configure the A2B bus? No, you don't need to add any kind of USB module to our analyzers. The bus analyzer and the AP both connect over USB directly to the PC. So you would just connect the bus analyzer to the PC, and then the bus analyzer app will hopefully detect it, and you can connect to it. I think we've answered all the questions. So I just want to thank you all for your time. If moving forward you think of more questions when you get to implementing your tests, please feel free to write to us at the email addresses shown here. And if you particularly want to address something to me, you can say, hi Ben, and it will just say you attended the webinar and you were wanting to talk with me.